So let us see the introduction to torsion. In all the mechanical machines, there is a prime mover which produces the power, and it is then transmitted from one point to another point, right? So there are different types of mechanisms that are used for this transmission. And in all this, the power is usually transmitted by rotating members. To be specific, the shafts, right? These rotating members transmit power by applying a turning force. For example, I have a electric motor. The shaft of the motor, electric motor is my prime mover. The shaft starts rotating whenever I supply the electricity to the motor, and this power, which is rotating in the rotating shaft, I need to transfer to my machine, for which I may use gears, belts, or some other drives, right? So when I use a gear or a belt, there is a force which is applied to the driven member from the driving member, right? And this force tries to rotate the driven member. So that is what we are trying to say. The rotating members transmit power by applying a turning force. And this turning force multiplied by the perpendicular distance, which is usually from the center of the shaft to the point of application of this force, that is your perpendicular distance, is called as torque. As a result of this, the shaft is subjected to torsional shear stress. In the previous unit, when we were discussing about shear stresses in beams, I had explained that there are two types of shear stresses. One is direct shear stress, which we have discussed already. Direct shear stress is, see, when you have a component and you apply a force which is normal to the cross section of the uh, component, right? So the kind of stresses that are produced there are called direct shear stress, because the component, the force is trying to directly shear the component, right? Whereas here, in case of torsion, when you are transmitting the torque, right, we are trying to twist the shaft, and in this, when the shaft is being twisted, the shaft material resists the twist, and because of which the shaft can get sheared, right? So the kind of the nature of failure is also shear here, but the stresses are called as torsional shear stress. The way we calculate the magnitude of the stress is completely different from direct shear stress. Direct shear stress is load by area, shear load divided by cross sectional area. This is not load by area, it is different, right? Now let us try to understand how to calculate these torsional shear stresses in any component. Now here I have considered a shaft. I have fixed one end and the other end is free, where I am applying a torque equal to T, right? Now because of this torque means you are twisting the shaft. Because of this, uh, now on this surface of the shaft, I have considered a line CA. This CA is shifted to CA dash. That means there is a twist in the shaft, and this twist angle is phi, and at the center of the shaft it is theta here, right? So with this arrangement, let us try to derive the expression. Let T be the torque applied, L is the length of the shaft, R is the radius of the shaft. This is what I explained. I imagined a line on the shaft, and due to application of torque, this CA is shifted to CA dash, right? Now this angle ACA dash, right? that is phi, and AOA dash, that is this angle theta. Let tau be the shear stress induced at the surface, right? At the outermost surface, the shear stress induced is taken as tau, and C is the rigidity modulus of the shaft material. The strain, uh, or rather I would call shear strain, that is induced on the component is defined as deformation per unit length, right? Now the deformation here is this, right? Initially it was at this point, now it has moved to A dash, and the length is L of the shaft. So I can write shear strain as A dash by L, right? So if I see, this theta is very small, right? When the torque is applied, the twist is very small. So this can be approximated to a right angle triangle, and I have taken this as tan theta. But theta, tan theta is very small, and we can say theta, tan theta is equal to phi. Also, arc length A dash, that is this, is r theta. Therefore, we have phi is equal to A dash by L, which is r theta by L. And rigidity modulus is defined as shear stress by shear strain, that is tau by phi, or from this I can say phi is equal to tau by r, shear stress by rigidity modulus. Now I am equating this and this equation. So we get phi is equal to tau by c, which is equal to r theta by L. I'm just rearranging it as tau by r is equal to c theta by L. C is the rigidity modulus. In some textbooks, they also use this as G, capital G, right? So you can use both C or G, whatever. So this expression gives me the shear stress at the outermost layer, that is at the surface of the shaft. So shear stress divided by radius. Radius is the distance of the outermost layer of the shaft from the shaft center. C is the rigidity modulus. Theta is the twist in the shaft, and L is the length. This is the intensity of shear stress at the surface, which is at a distance r from the axis. Now shear stress at a distance of x from the axis is given by, instead of r I am replacing it by x. So tau x by x will be equal to c theta by L, and that will be equal to tau by r, right? So at any distance from the center of the shaft, if you want to calculate the shear stress, you can use this formula. Okay. Now let us see what is the strength of the solid shaft. The strength of solid shaft or strength of shaft is actually the maximum torque or power it can transmit. Now I have considered a solid circular shaft here of radius r, and the permissible stress in this, or the stress induced in this shaft at the surface, I have taken it as tau. Uh, Consider a small elemental ring, right, in this circle, in this circular shaft at a distance of x from the center, and the thickness of this element can be taken as dx. Now the area of this element, that is this annular region, see, this is very small element. So if you just cut this and open, you will get it as a rectangle. The length of this rectangle will be the circumference of this circle, that is 2 pi x, 2 pi r basically, and the depth of the rectangle will be dx. So dA, that is the area of element, will be 2 pi x into dx. And the shear stress developed at this section, we have derived this equation in the previous section. Tau x by x is equal to c theta by L. So I'll be using here tau x by x is equal to tau by r, or tau x is equal to tau into x by r, right? The turning force at this section, turning force is, see, the shaft is transmitting the torque. The torque transmitted is actually the force at the circumference of this shaft multiplied by this distance. Now I am considering this small element. So what is the force at this point, right? This circle. So that is given by shear stress into area. Now shear stress is tau x. Uh, so I'm just substituting these values. Tau into, actually it should have been dA, not dx. uh, Tau x is tau x by r into dA, and dA I have it as 2 pi x dx. Now when you substitute all this, the final expression you get is 2 pi tau by r into x square into dx. Now the torque or turning moment at this point at x is turning force into perpendicular distance, right? Turning force was 2 pi tau by r into x square into dx. Multiply this with another x, so you get 2 pi tau by r into x cube dx, right? 2 pi tau by r, this is a constant, right? It does not change, so I'm keeping it as it is. Now in order to find the total torque, we have to integrate this equation from the limits 0 to r. 0 is the center of the shaft, r is the outermost surface of the shaft. So when you do this integration, so I get like this: t is equal to 0 to r 2 pi tau by r. So this is constant, it will remain as it is, into x cube dx. Now integration of x cube will be x power 4 by 4 with within the limit 0 to r. So it will be r power 4 by 4, right? T is equal to 2 pi tau by r into r raised to 4 by 4. This r gets cancelled, and what remains is, and 1 2 gets cancelled here, so pi tau r cubed by 2. Now r is actually d by 2, so I'm substituting this here. So this will be d cubed by 8. So 8 into 2 will be 16. So the torque transmitted by a solid shaft is pi d cubed by 16 into tau Newton mm, where tau is the permissible shear stress. Now if you want to find the shear stress induced in the shaft when it is transmitting a torque T, then it will be 16T by pi d cube. Tau will be equal to 16T by pi d cube. You can use either ways. Now the same expression we can find it for a hollow shaft. For a hollow shaft, there is a hole in the center, right? So it is a solid shaft with a hole in the center. So generally we use hollow shaft in order to decrease the weight of the shaft, because see, if the weight increases and the shaft length is long, then there can be sagging in the shaft because of self weight. So we need to we need to decrease the weight of the shaft. That is one reason. Another reason is the rigidity modulus. Sorry, not the rigidity modulus. The rigidity or the strength of this hollow shaft is comparably higher of a solid shaft for same weight to length ratio. For this reason, in many of the applications we use hollow shafts. For example, in the lathe, right, the spindle, main spindle of the lathe, it is a hollow shaft. The power transmit axle, wheel axle, is a hollow shaft, right? So there are main transmission shaft of the vehicle, not the axle, sorry. Transmission shaft of the vehicle usually is a hollow shaft. So that is for this reason. So in the same lines, right, how we did here, what we have to do is you consider an element at a distance of x and its thickness is dx, and you have to integrate between the limits small r, that is the inner radius, and capital R, right? So when we do that, you get the equation as T is equal to pi by 16 tau d raised to 4 minus small d raised to 4 by d, right? So this is the expression for finding the torque transmitted by the hollow shaft. So we are talking about strength of the shaft. So we need to also know the power transmitted, and power transmission transmitted is given by 2 pi nt by 60 in kilowatt. So you will get in kilowatt when you put torque in Newton meter, kilonewton meter, right? So that is when you get in kilowatt. If you put it in Newton meter, you will get it in watts, right? Accordingly, you have to balance the units. Uh, Now we will discuss about the torsion equation. We have tau by r is equal to c theta by L. This is the first expression we have derived earlier. And the torque transmitted by the shaft is T is equal to pi d cube by 16 into tau. So from this, I can find tau as 16t by pi d cube. Now I have t here and sorry, tau here, and I have found tau from this expression. Now I will substitute this value of tau in equation 1. So when I do that, we get 16t by pi d cube, and r is actually d by 2, right? So into d by 2. Now this 2 will go to the numerator and it gets multiplied as 32t by pi d raised to 4. This p cube and d becomes d raised to 4, and that is equal to c theta by L. Now this 32 I am taking to the denominator of this pi d raised to 4 by 32. So P by pi d raised to 4 by 32 is equal to c theta by L. This term pi d raised to 4 by 32, it is called as the polar moment of inertia, and it is represented by the letter J, capital J. So I can write this as T by J is equal to C theta by L, and C theta by L is equal to tau by R from this expression we derived in the beginning. So T by J is equal to C theta by L is equal to tau by R, and this is called as the torsion equation. Okay, so this is similar to our bending equation, right? Uh, but this is applicable when a shaft is subjected to torsion.